Until now, we have only looked at the case of uniform torsion. Well, if you think about the application example we did, that is actually a non-uniform torsion, that in different parts of the shaft you have different torques which are acting. But even in that case, what the problem specifically asked, we looked at individual segments. We did not look at the phi or the angle of twist of the entire segment. So piece by piece, the shaft is still uniform. But when you zoom out and you look at the shaft as a whole, that particular case, it is a case of the non-uniform. This particular topic, what we are going to focus on in lecture, we'll look at non-uniform torsion, on how to compute the angle of twist and so on, and we'll also look at indeterminate problem. And your savior for this topic, you'll be surprised to hear this, your savior for this particular topic is going to be what you have learned in the pure axial loading. Now, as I told in the beginning of the this lecture or in the introduction, is that although these loading conditions are more or less completely different, one of them deals with just pulling or pushing, right, and the other one deals with torsion. Although these loading conditions are different, there are certain analogies that can be drawn in terms of how the deformations happen, that will help you immensely just analogically to derive that what is going to be the angle of twist or some of the other parameters which are. Let's go ahead and first take a look to what is the analogy, and then let's see that how this analogy will help us in easily solving the problems related to torsion. So first I would like to jog your memory in what we have already learned before. We have learned the axial case and we have learned the uniform torsion case in the last couple of lectures that you have seen. Now for the axial case, remember this was our axial case, very simple, a bar which load P at one end and the P at the other end to keep equilibrium. For this one, what we had seen that our delta, remember delta was the deformation of the bar, was equals to P times L divided by A times E, right? Very simple, L divided by AE. Now if you recall what we learned in the torsion until now, that our phi, that is the angle of twist, remember the torsion formula, the last thing that we derived, P is equal to P times L divided by A times G. Now can you start seeing the analogy in between these two formulas over here? Take a look again. Delta is here and here is phi. So both are somehow measurements of deformation in some sense, and delta is the longitudinal displacement, phi the angle of twist. So some measure of deformation, right? Then coming to the right hand side, here you have P, which is the applied force, and here you have T, which is the applied torque, right? Both of these formulas depend upon the length of the member L. So here I have the length of the member L, here I have the length of the member L over here. Now let's come to the denominator. In the denominator, here you have A, correspondingly here A was the area of cross section, here you have the J, which is the polar moment of inertia, and here you have the Young's modulus E, and here you have the shear modulus G. And analogically also, if you see, these formulas look more or less the same. So delta PL by AE, P PL by JG, right? They look more or less the same. Analogically, they are predicting the same thing. One of them is predicting the longitudinal deformation and the other one is predicting the angle of twist, right? Okay. Now, going a step further, do you remember that what this particular terminology was called? AE? Yes, it was called the axial rigidity, right? And why was it called the axial rigidity? Because if you have a structure where your A is high, E is high, you will have the delta as smaller and smaller because it's inversely proportional, right? So it is making your shaft or your rod more rigid to deformation. That's why you have the axial rigidity. Similarly, if you come to the right hand side over here, take a look at the denominator, JG, right? This JG that you have, the higher the value of jg, lesser will be your angle of twist because it's inversely proportional to phi, right? And also higher the jg means you are making the structure or making your circular shaft in this particular case torsionally more rigid to resist this angle of twist that you have. So what is jg going to be called? You're right. If AE is axial rigidity, jg as torsional. You see so many similarities. Torsional. Now you will see that once you have established this analogy, some of the concepts that you have studied in axial loading, for example, the indeterminate structure, right? When you had structures where you had uh, non-uniform axial loading. So you will see that similar cases can arise in the case of torsion, and analogically you can solve it in a very similar way. So let's go ahead and take a look at some of the problems. For example, the first one. Do you remember the axial case what I have given here? So we are going to look at non-uniform torsion, but please recall the case of the non-uniform axial loading. It is still determinate over here, but for this one, do you remember that the delta that we had calculated, how did we calculate the delta? Here what we had done is that we had at every section, every discontinuity that was there, in between those discontinuities we had cut the cross sections, we had calculated the internal forces N and our eventual delta, that is here, this total delta of this whole bar. So here this delta is actually delta AC, right? Delta AC was sum of the deltas of these individual portions, right? So if my from A to B over here was maybe portion 1, if B to C was portion 2, then I can go ahead and write that delta AC, that is the total delta, is summation of delta I over here, which is delta 1 and delta 2, which becomes equals to Ni Li by Ai Ei, right? Now come to the torsion problem and see analogically how much it is going to help you. In this torsion problem, what you have, it's a non-uniform torsion. You have different torques acting at different points on this particular shaft that is there, A, B, C, D. Now this shaft, remember, it has a circular section and it has another circular section which has a higher cross-sectional area. So it is non-uniform from that perspective as well. So here, how are we going to solve it? Exactly in a similar fashion as we solved here. Here also, what I'm going to do is that I can come and then I can, in between the discontinuities, I can cut the sections, right? So here I will have 3 sections here, right? So for the first one, second one, third one, right? So for the first one, I can draw the free body diagram. Now if I just separate out this part over here, on the left I have a T1, and suppose the internal torque TAB, let me call the internal torque as TINT maybe, just for the sake of discussion. So the internal torque TINT in the section 1 is TAB over here. If I cut another section 2 over here, the internal torque there is TBC. So here TINT, 2 is your T over here. And lastly, if you cut a torque over here, now remember here also, if you want to make your life simple, you probably should just take the right hand part of this shaft to draw the free body diagram. Otherwise, you can do here as well. So here also I have T internal 3, your TCD, right? Now going back in the similar analogy as we had over here, in this particular case, what is going to be my P for section 1, for this part 1 over here, which is between A to B, that is part this is the angle of twist in A, P, right? What is this going to be? This is simply going to be nothing but the same formula, the torsion formula, that is the TL divided by JG. Now I am going to consider the internal torque as I did over here. I consider the internal axial forces. So it is going to be T1, right? times that length of that particular section times LAB divided by J of AB. Remember, the J, the polar moment for circular shaft, depends upon the radius, times G, right, of AB. If suppose they are made of different materials, they have different shear modulus. So similarly, you can calculate your phi of 2, which is for the section B to C, then phi of 3, which is for the section C to D over here. So what is going to be my total phi? Remember, total phi is the total angle of twist that you are having from the one extreme to the other. Here this delta was the total deformation from A to C. Here the total phi is going to be from A to D over here. So my total phi, right, if I have to further explicitly write, from A to D is going to be summation of the Pi, right, which is simply going to be my summation of P, each internal torque, comma I, times the length of each of these segments. In the first one it was LAB, then LBC, then LCD, right, divided by JI. So you see, analogically it is so similar. So if you have properly understood and if you have learned the derivation for the axial case, doing it for the case of the pure torsion is actually pretty. Let's go ahead and look at some of the further analogies which are there. Remember this one where we had the continuous gradation of the area, and if you have a body force that is being applied, we had cut a small section dx and calculated the internal forces and so on. Here also it is going to be exactly the same thing. In the axial case you calculated the deformation. In this particular case you are going to calculate the phi, and you can take the free body diagram and you can calculate it and you solve it, and you see that eventually the integral comes out to be one and the same. Analogically again, going to be 0 to L, right, T internal point x divided by a x, right, assuming it's made of the same material. So analogically again, very similar to what we had derived over here. Internal force, internal torque, length of dx divided by the modulus of shear modulus times the your polar moment of inertia, right? Okay, all right, so let's move ahead. Now remember that we had also seen for the axial case that the stresses on the inclined section. So how did we do that? In that one, what we had done was that we had taken section cut at a certain angle for which the normal was making a certain angle of theta, right, and we had looked at two extremities for which the normal force becomes maximum and the shear becomes maximum. See, this is also was the section where we sort of looked at that if a bar is under pure axial loading, it is not true that no matter where you look and how you look in the bar, all elements are going to be under axial loading. It depends upon the angle you are looking at, right? So if you are looking at an angle which is perpendicular the longitudinal axis, then yes, you are only going to have the normal stresses. But if you are looking at elements which are slanted at a particular angle, right, which you have one particular theta, they are going to have both the axial as well as the shear strains. Couple of special cases for that was that that shear strain becomes maximum when the theta was equals to 45 degrees. So if you had taken an element like this over here, where all the faces were 45, 45, 40, 45, like in between you have the 90-degree angles over here, right, you were having this element which was having a normal force of sigma x over 2 and a shear force of sigma x over 2. Now remember, shear force equals to sigma x over 2 did not mean that the shear force has become a normal force. It just means the magnitude of the tau has become the normal force divided by 2, right? Now let's look at the case of the torsion. In torsion, if you do a similar thing, here in the torsion also, if you take an element which is perpendicular to the longitudinal axis, right, this element over here, you are simply going to have the torques simply going to have the shear stresses tau. Here when we took a perpendicular element, it was just the sigma x because of this p. Here, because of the applied torque, my all these rectangular elements on the surface of my member are in a case of pure shear. If I take any element whose face perpendicular to the longitudinal axis, I am going to get this tau over here, right? This is in 3D and this is in 2D. So the 3D diagram, if you have taken a small chunk over there, and this is 2D. I'm looking at it. Now, as I did over here, if I come to this particular member now, and if I start cutting angles at different slopes, right? What do I get? Let's see. If we start cutting angles at a different slope, so here I am not going to go into the further details of deriving all these equations and arriving at the final formula. If you can take a look at any standard textbook, it is just a lot of algebraic bookkeeping that is going to happen. But I am going to give the gist of it, following which it is very easy to draw to write the equilibrium equation. So here what I have done is that we have cut an angle, we have cut this member over here, the entire section plane, to which the normal, so this is your normal vector which makes an angle of theta to the horizontal, exactly in a similar analogy to what we did for the pure axial case. Now once you have that, and from the stresses you like the forces, remember this particular phase by A divided by cosine of theta and so on. In the end, what you get, that is for this kind of a configuration, what you will get, this sigma theta that you see over here boils down to tau sine to theta, and your tau theta, this particular shear over here, becomes equals to tau cosine of 2 theta. Now what can you sort of decode from here? See, what we hypothesize, that if I was taking the plane which was perpendicular to my longitudinal axis, right, I did not have any axial stress, I had only shear tau. So that means if my normal is exactly aligned here, that is my theta equals to 0, right. So if in these equations we put theta equals to 0, what do I get? I get tau of theta equals to tau, and I get sigma theta when theta equals to 0 becomes equals to 0, it vanishes. So I get back to what was my original configuration there, right. That's the case where you're taking an element like this. Now the question is that so for this configuration your sigma is 0, sigma theta is 0, right, because if you put a 0 over here it becomes 0. For what angle or what theta here does my normal stress become maximum? This normal stress sine to theta, the maximum value is 1 over here, and it becomes maximum when again, when similar analogically, when theta equals to 45 degrees. So maybe let's just write it over here. So sigma theta becomes equals to sigma maximum at theta equals to 45 degrees. So what happens at 45 degrees? If I put a 45 degrees over here, in that case this one becomes sigma max becomes equals to tau. Again, please be clear about this, that sigma max equals to tau doesn't mean that your normal stress is becoming shear stress. It is just that the magnitude of the normal stress becomes equals to the magnitude of the shear stress that section experiences when applied to the torque T over here, right. And at theta equals to 45 degree again, what happens to my tau of theta? Very interesting. At 45 degree, this cos 2 theta becomes cos 90. So tau of theta at theta equals to 45 degree becomes 0. So essentially shear vanishes, right. So tau of theta at theta equals to 45 degrees comes tau of theta becomes equals to 0, right. So how does that look like? So if you take a look at this one, how it looks like is essentially something like this. If I am taking an element to which the perpendicular, for which this section is perpendicular longitudinal axis, I have only the taus across the faces, no axial stress. Whereas if I am taking a 45-degree angle, as I just derived in the previous page, I am going to have thing like this over here. I am going to have a maximum sigma, which is going to be equals to this tau over here, right? And my shear vanishes. So it's such an interesting scenario where you are having this circular shaft where every rectangular element is having pure shear, but within the same shaft, if you are looking at an angle of 45-degree, those elements aligned at 45-degree are only experiencing normal stress, right? And this is again very important when you are applying torque to members are poor in tension and compression. Remember, this sigma over here is nothing but a tensile force, and this sigma over here is nothing but a compressive force, right? So even though your material may be good in shear, if the material is particularly weak tension or in compression, classic example are some brittle materials. In that case, you are going to have a failure, right? A classic example I will show you right now using our very common classroom chalk. So this is a classroom chalk, right? So to this chalk that is there, if I am applying a torsion at both the ends, I am not pulling or pushing, I am simply applying a torsion, and this is a brittle material which is weak in tension as well as compression. Mostly in tension, compression it may be better, but if I just apply this one, and if you see at what angle it failed over here, it failed at that 45-degree angle. Over here you see this kind of an angle which it has made over here, and similarly you can see over here, right? So this one fails at an angle of 45-degree. This material may be good in shear, but and how can I tell it is good in shear? You take a piece of chalk and you take a knife and you try to cut it. You will experience substantial amount of resistance, which tells me that this piece of chalk is probably quite good in shear, but this chalk again is not very good in tension, or maybe in compression. Mostly in tension it is not very good. That's why when I applying the torque at those locations, at those angles, right, where I'm having this maximum tau. So this is again the figuratively, if I have to explain, you start to have the crack at the 45-degree plane and the chalk snaps at 45-degree angle. When some of you go back to your the campus, you can try to do this experience you can try to do this experiment rather classrooms. That is, it's a fun experiment, right? Okay. So the last thing on this topic is that, so we have looked at the non-uniform case, non-uniform but deterministic. Then we have also looked at the stresses at the inclined sections. The last case, which is over here, is the statically indeterminate case. So what you see in this statically indeterminate case is that, similar to the axial loading case, you have a shaft which may have different cross section, and it's clamped at this end and this over here. So these points A and B do not move relative to each other. That means if you calculate the phi AB, the relative movement of B with respect to A over the total angle of twist is going to be equal to 0, similar to what you had in one over here. So remember here my compatibility, and we are going to again remember the equations of compatibility, that your delta AC for this particular portion and delta BC for this particular portion was overall equal to 0. That delta AB was delta AC plus delta CB was equals to 0. And you had maintained the equilibrium and so on, and you had eventually derived what are the reactions. Similarly, for the case of the torque, we can also write the equilibrium equation for this one. Here you see the internal torque T naught. Now the directions are important. If you do your finger curling for the T naught, you will see that the double arrow for T naught points towards this direction, and these are your reaction torques that you have here. So I can write here, I have my TA plus TE equals to 0, right? And what is the compatibility? The compatibility is that your phi of AC, the first part, phi of AC plus phi of CB, the total P, total angle of twist between A and B, that is equals to 0 because those two ends are clamped, right? So we have the phi of AC plus your phi of CE will be equals to 0. Now, if you write it a few steps further, what do you get? What you get is your P of AC is nothing but T, the internal torque which is acting over there, that is T, I am going to write T internal AC times length of AC divided by J of AC times G, assuming the material is the same throughout, right? And plus is going to be for this one here, going to be T internal EB times length of CB divided by J of CB times G, right? And this equals to 0 over here. Now you have two equations, this equation over here and this equation over here. Of course, you realize that this internal torque you have to write in terms of what you get here. For example, for the section AC, if you cut a section over here and if you draw the free body diagram, how does that look like? The free body diagram would be on the left you have torque A, the reaction torque that is acting. So to compensate that in the section AC, so this is my section AC, right? To compensate that on the right side, I must have the balancing torque, that is internal E must be equals to A, right? Similarly, you can write for the section CB, so you will have two equations. So eventually this equation you can write in terms of the reaction or the torque which is applied, and you have another equation over here. You can solve both of them to get the reactions that you want. You can get those internal deformations also. You can get the phi AC, and you will see when you add them up it must equal to 0 because you have to satisfy the compactness. Now that we have learned about the cases of the non-uniform torsion and the structures, the indeterminate structures under the torsion problems, let's go ahead and look at one application example.